Hi, welcome to part B of chapter 5. Today we are going to look at section 5.6, Hess's law, section 5.7 enthalpies of formation, pond enthalpies, and the energy food value in section 5.9. In the last section or part A, we went as far as section 5.4, calorimetry, that is the measurement of enthalpy of reaction at constant pressure. There are two examples, one or two examples I want to revisit before we get started with section 5. 0.6 Hess's law. And these are the examples I want to go through is example on 5.6 example 5.6 measurement of enthalpy of reaction using the coffee cup calorimeter. This is determination or determination of enthalpy of reaction at constant pressure using calorimeter, which you will use in the lab or you may have used in the lab. Since this is an example, I'm just gonna zoom this so that you can see the numbers. Assuming that this is an experiment in the lab, which I know for sure this is what you will do in experiment number 10, and the lab is of reaction, where you will react HCl with sodium hydroxide, hydrochloric acid, sodium hydroxide, acid-base neutralization reaction. All right, let's see. When a student mixes 50 ml of 1.0 molar HCl with 50 ml of 1 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the resultant solution increases from 21.0 to 27.5. Let's stop here. The moment you see that the temperature increase, this means it is exothermic reaction. Exothermic reaction, reaction which gives away heat, and the symbol for enthalpy for this will be negative. So point to consider here before we move forward is increase in temperature is an evident or sign or criteria by which you can classify a reaction as exothermic. Temperature is increasing. So we are asked to calculate the enthalpy of enthalpy change, which is delta H, for the reaction in kilojoules per mole of HCl, per mole of HCl, not per mole of sodium hydroxide, per mole of what? HCl. This is acid-base neutralization, and one of the product is H2O. That's why we are given the specific heat of H2O, 4.18 joules per gram per Kelvin. I'll just ignore the Kelvin and assume that it is joules per gram per what? Per degrees Celsius, so that you reconcile with the change in temperature. The reason why you are given density here so that you find the mass of the solution. Remember, Q is the same as the change in enthalpy for reaction. So the reason why you are given this is if you have 100 ml of solution, where is 100 coming from? It is 50 plus 100. Let's see how to proceed with determination of enthalpy change. So this is a reaction. The ratio is 1:1. Mole ratio is 1:1. Recall, enthalpy change is the same as Q, which we know. Q is given by, Q for the reaction is given by specific heat times mass of the solution times change in temperature. CS, understand that this is a specific heat. The symbol for specific heat is CS. Remember, C in the previous section, denote the heat capacity, but CS is the specific heat, time is the mass of the solution. Not always that, the density of solution is one, it could be a different solution. Please recall the density equation. Mass is given by volume times the density. Therefore, 100 grams is from calculation, manipulating the density formula times the change in, well, you can just, I know you're wondering how do we move from degrees Celsius to Kelvin. Either way you use degrees Celsius. I prefer using degrees Celsius because we are using degrees Celsius in the lab. But if you want to stay with the SI units, use K. It turns out that it is negative 2.7 times 10 raised to 3, or 2.7. What I want to mention here is that the negative is because it is exothermic reaction. Quite often, as I mentioned before, students bubble out, they use the right equation, they know they study so hard, but they forget to use the right sign, okay? Please, when you see increase in temperature for such kind of calculation, always remember the sign. Ask yourself, is it exothermic or is it endothermic? So that will be what? This will be negative 2.7. Don't bubble out to positive 2.7. If this is going to be one of the question in the exam, it is negative 2.7 for exothermic reaction, So change in enthalpy is the same as the heat of reaction at constant pressure. The subscript P here stands for constant pressure, and Q is the heat of reaction at constant pressure, which is the same as change in enthalpy for reaction. And the reason why we have negative here is because it's exothermic. It was not mentioned anywhere that it is exothermic, but because there was increase in temperature, which means the reaction was emitting or giving away heat. Now, if you recall from the question, we are asked to calculate per mole here, reaction per mole of what? Per mole of HCl, which means we need to find the number of moles. And using the molarity equation, okay, in chapter 4, remember, molarity equals to number of moles, all right? Number of moles of HCl over volume in liters of HCl, which means number of moles of HCl is given by the molarity of HCl times the volume in liters of HCl times the volume in liters. So if you look at this, we had to change the volume to liters. Molarity, we were given that, and this is the number of mole. So if we divide that per mole, it's gonna be Q for the reaction. And remember, it's negative over the number of moles of HCl. If it was for sodium hydroxide, we'll just have to plug in there. So remember that you have to divide by the number of moles. Q for the reaction of the number of moles is negative 54 kilojoules per mole. So that's what I wanted to just recap from what we looked at last time. You can try practice exercise 1 on your own, all right? Please try that and see how the answers look like comparing to what we have in the book. One more example before we shift to 5.6 is suppose you are asked to find the change in enthalpy or enthalpy change of this reaction, that's precipitation of silver chloride. when 50 ml of 0.100 molar silver nitrate and 50.0 molar ml of 0.1 molar HCl are mixed in a constant pressure calorimeter. The temperature of the mixture increases from 2. So again, this is exothermic reaction. It's exothermic reaction because of what? There is increase in temperature from 22.30 to 23.11. Okay, this is the balanced equation, means 1 mole of silver nitrate react with 1 mole of HCl to precipitate 1 mole of silver chloride and 1 mole of nitric acid. This is neutralization specific heat given here. For this, calculate the enthalpy change for this reaction in kilojoules per mole of silver nitrate, So change in enthalpy for reaction is the same as Q for P at constant pressure, where, all right, Q E or reaction, the mass of reaction times the specific heat times change in temperature times change in temperature. We are mixing what? We have the mass of the solution, we have the specific heat. Change in temperature is given by T final minus T initial. T final minus T initial, which is 20 what? It is 23.11 degrees Celsius minus 22.30 degrees Celsius. And here we have change in temperature is 0.81 degrees Celsius or 0.81 Kelvin. So that if we go back here, we'll just have to plug in the values and say what? 100 grams of solution times specific heat ECS, which is what? 4.18 joules per gram times K. So I'm just using, oh no, we use degrees. So here we can say, let's use this right here. So that we say grams times degrees Celsius times change in temperature to 0.81 degrees Celsius. If we cancel the units, grams and grams will go away, degrees and degrees will go away. And we are left with final answer in joules. If you multiply that, this will be 67.7. This is 60. If you multiply that, this is going to be not 67. I meant to say this will be 338.58 joules. This is the joules. If we change to kilojoules, all right, changing to kilojoules, 0.33, or rather, if you want to change that, this is what we have, okay, 338.58, we convert using this. Some of you may wonder, how do you change from joules to kilojoules? 8 joules. This is the conversion factor. For 1,000 joules, we have 1 kilojoule, or 1 kilojoules equals 1,000. So that this and that will cancel, and the answer is 0.333858 kilojoules. So we have changed to kilojoules because the question was in kilojoules, per mole. So if I know that, we need to find the number of moles of silver nitrate, NO3. All right. We have to use the molar mass or no molarity. Okay, molarity. We have 50 ml. Therefore, number of moles given by molarity of silver nitrate, all right, times volume in liters, which is equals to 0.050 liters times 0.100, and we have 0.005 0 moles. This is the number of moles of silver nitrate. So that change in for the reaction is given by Q for the reaction over per mole, which is given by negative. This was given up negative 0.33858 kilojoules over 0.005 moles. Okay. This is moles of silver nitrate, HENO3. I'm dividing it by the number of moles, and it's out to be negative 67.7 kilojoules per mole, kilojoules per mole. So remember to use the right sign. Why am I having negative at the end? This was negative for exothermic reaction. If it is being given off, all right, always the sign is negative. If this was an exam, I know somebody somewhere may make a mistake of just bubbling out, or if it is face-to-face, bubbling out on the Scantron, all right? Or if it is online, in this case, you don't want to pick the wrong multiple choice. Don't pick the positive. I know examiners, whoever make this exam, online exam or questions or homework assignment, they pick two multiple choice with different signs. One could be positive, one could be negative. So be careful with the sign notation for that, right? Let's pick up from here. Please go back and practice on our calorimeter problems. Look at the worked example in the text before you attempt the homework assignment online. You should try on your own. Hess's law. Hess was Hess was a scientist, all right, who is credited for writing the first he write or help in the formulation of the principles of thermochemistry. He was a German. He came up with a principle by which, or a law by which we can determine the enthalpy of reaction. Some others call this Hess's law of heat summation. Summation, you know, summation when you add things, okay? And this law is basically used in determining the overall enthalpy of reaction. If you have more than one reaction, we can determine the enthalpy. Remember this term here, this thermodynamic term, enthalpy change or change in enthalpy. If we have more than one reaction with known enthalpies of reaction, we can find the sum those to get the overall. We can calculate the change in enthalpy here using the published values and properties. You'll be given these values, and I'll show you when we get to an example on how to use that. If a reaction is carried out in a series, look at this. Series, that means we may have step number 1, step number 2, step number 3. This means delta H1, delta H2, delta H3. That means we have different steps. Step 1 with its own enthalpy of reaction. Step 2, its own change enthalpy of reaction, and then the summation now. All right, overall reaction in this case, you see this overall reaction here, change in enthalpy for the reaction is given by 1 plus enthalpy for 2 plus change in enthalpy for 3. It's give us for overall. We get forward for overall reaction for individual steps. This is just, some of the this is an illustration on finding the overall reaction. Doesn't really matter how many steps you take before you get to the final product. In this case, we can have methane and oxygen in combustion reaction to produce CO2 and H2, or we can have steps. See the first one and second step. But overall, we have the same change in enthalpy, same change in enthalpy. What does SS law entails? You'll be given series or steps before the overall. Here is an example on 5.9 that if we have several steps, if I look here, this is ethene reacting with oxygen and its enthalpy of reaction is negative 1299.6. This is step 2, this is step 3. And the question is, what is the change in enthalpy for this reaction? In SS law, all right, in SS law, you want to look at each individual step and reconcile with the overall reaction, overall equation, and see how each individual has been manipulated, and later on we will calculate. What I mean by reconciling the overall with each individual is looking at the product and the reagent. For example, to arrive at this thing here, it means equation 1 has been flipped. You have to flip the equation in order to have this as a product, in order to have that as a product. So if that is the case, we will flip equation 1 and recall the properties of enthalpy of reaction, or just enthalpy, that if you reverse, you're gonna reverse or change the sign. So this will be positive if we reverse this. If I look at carbon, solid carbon, the only step with carbon is equation 2, and there is a coefficient of 2, which means we multiply equation 2 by what? By 2. A coefficient of 2 here, coefficient of 2 here, coefficient of 2 here, which means we will also multiply this by 2. I think this will remain the way it is because I see hydrogen is still hydrogen. So with this kind of, approach, we are using SS law to find the enthalpy change for the overall reaction. So with this, let's see how this has been put together to get the overall. So we had to flip equation 1. If I go back here, this was the product. I mean the reactant, but it's now the product. We flip the equation. And if we flip, this has changed to positive. It was negative. It was negative, okay? We multiply this by 2, which means we will also multiply this value by 2. Please don't forget to multiply by 2 the enthalpy. If you are dividing it by 2, you'll have to divide by 2. This one is just the way it is. I don't think we had to do it. You see this, we have nothing to do with equation 3 because hydrogen here is the same as hydrogen here. So we know we will leave equation 3 the way it is, but we put here. Now we cancel what we can cancel, but we don't do anything here. It's gonna be what? Oxygen gas, half of it will go with half. That means, see 1/2 here. 2 is 2.5, which means 0.5, a half will go with half, and then 2 will go with the 2 here. Liquid H2 will go with the liquid H2, CO2 will go with the CO2, and we have the overall equation. So you cancel what is common on either side. What happened here now is how we arrive at this number is just adding everything. Just adding to get this value is enthalpy change for step 1, and enthalpy change for step 2, and enthalpy change for step 3. So this is step 1, step 2, step 3, and this is just overall enthalpy for reaction. That's why I say sometimes it's called the heat of summation, Hess's law of heat of summation. So to be well-rounded in this concept, you need to recall the properties of enthalpy. When you flip the equation, the sign also changes. When you divide by an integer, we also divide the change in enthalpy by that integer. If we divide by a number, we divide by that number. If we multiply by that number, we multiply the number by the same value across, and then we add everything to get what the overall change in enthalpy for the reaction. So that's all about the heat of summation, Hess's law of heat of summation. So if I look at this, let's look at this. For example, just the way we did the other one in the worked example, from this enthalpy of reaction, this is step 1, this is step 2, this is step 3, all right? If I look at the overall, this one, calculate the change in enthalpy, I meant to say change in enthalpy for the reaction of ethylene with fluorine, molecular fluorine. This is the overall reaction. From the 3 reactions, this is the overall reaction. We are asked to find its change in enthalpy. If we do the reconciliation of all these 3 with the overall, I see that C2H4 is the reactant. Where is it here? It's nowhere. It is in step number 3, but we have to flip. So that means in step 3, we will have C2H4 gas going to 2C plus 2H2, and then this is gas, this is solid, and change in enthalpy for this will be what? It's gonna be now negative 52.4 kilojoules. Right, let's see. If I look at fluorine, okay, and also, all right, and also the high HF here is product on this side, but we have 4 moles of hydrogen fluoride, 4 moles, but we have 2 moles, which means equation 1 was multiplied by what? Pi 2. So if I multiply by 2 equation 1, all right, equation 1 will be 2H 2 gas plus 2F 2 gas, right, going to 4H F gas. And then when I multiply that by 2, 537, all right. If I multiply by 2, I have my calculator here. I need to multiply by 2, 537 times 2. I have here 107 for 1074 kilojoules. 107 kilojoules. The reason why I multiply that by 2 is I'm looking at equation 1 and ask myself, how will I end up with this? Overall, multiplying by that. If you look at C4, all right, CF4 here, it is in equation 2, nowhere else, and it's on the product side, so we don't need to do it. We don't need to flip the equation. However, there is a coefficient of 2 in front of it, which means we multiply that by 2 across. So if I multiply that across, this will be 2 carbon CS plus 4. I multiply this by 2, 4 kilofluorine is in gaseous state, going to 2F, no, 2CF, all right. Here, 2CF for gas like that. And then we multiply that by, this is delta H, this was delta H, equals to, we will multiply that by what? By 26,680 times 2. I have negative 1360 kilojoules times 1360 kilojoules. So I do have now, if you look at the overall now, I will, if you look at the overall, right, we cancel this and this right here. We cancel this and we cancel that. All right, so if I add that, it's gonna be C2H4 gas plus 2 plus 4 is 6. That's where we have there 6 of 2. It's coming from here. 2 plus 4 is 6, going to 2CF gas plus 4HF, and then delta for the reaction is given by delta H1 plus delta H2 plus delta H3, which will give you negative 2.4 times 10 raised to negative 3 kilojoules. Please double check that. Make sure you get the right answer for that. 2.4 is exothermic. When you add everything from here, these 10, 52, all right, it's gonna give you 10.2. So please practice more on interlevel formation. I mean, Hess's law, and how to use Hess's law to find the interlevel chain for overall reaction. The only way you will know that this is Hess's law is when you are given series of reactions. Sometimes you may be given 3, you may be lucky to have only 2. If you have 2, and then it's very easy to manipulate. Sometimes you may have 4 equations, all right? In all of them, please just follow the steps I walk you through here, and you'll be okay. Let's move on to Endelabiso formation. Okay, 7.5.7. When we say formation, something is being formed, all right? So what should come to your mind when we talk about Endelabiso formation? Endelabiso formation, HF, you'll see this with the subscript here, all right? This is understood to be enthalpy of formation, enthalpy for formation, all right, of compounds, all right, from individual, all right, from individual. I meant to share my screen here. Let's see, something is happening here. Just want to make sure we are on the right page. Okay, so this is the enthalpy of formation of compounds, like that, compounds from elements. For example, oxygen, hydrogen gas to form H2O liquid. We can determine the enthalpy of formation for that. There are some tabulated values for that. We call standard enthalpy. This one, look at this subscript right here. This means standard. You read this as a standard enthalpy of what? Of formation, enthalpy of formation. And when we talk about standard, that means there should be some sets of conditions at, look at this, at standard temperature. Pressure, we call STP. There are some conditions you need to remember. That means one, or rather, pressure at STP is always 1.00 atmospheres. Temperature is 298.15 Kelvin, 298.15 Kelvin, or this is 25 degrees Celsius. If you look at this, 25 degrees Celsius, we use Kelvin for SI, and molarity for molar volume. Molarity, that's the concentration, 1.0 molar. If we have this condition defined, we are talking about the standard state. And when we talk about the standard enthalpies, we are working at this temperature. Always the temperature is 298. You are given, all right, on table 5.3, table 5.3, you are given standard enthalpies of formation of compounds. I'll give you in the exam, all right, this table. Let me just even blow this on up so that you can look at. If you look at this, these are just standard enthalpies of formation at 298. When we say standard, temperature is 298 Kelvin, pressure is 1 atmosphere, so that when we say standard enthalpy for this, you can either be given for specific compounds in a question, or I will allow you in the exam to use this table, or I may give you the enthalpy of formation of species in a chemical reaction, in a reaction. What I don't see it here is for elements, it's understood to be 0. The formation, for example, of oxygen gas. I have another table here with standard. If you look at the element, silver is 0. If you look at the element, this is bromine 0, carbon 0, calcium is 0 at elemental state 0. You got to know when it's 0 because that's an element that's responsible for forming compounds. We don't make elements, it's already there. We don't make those elements. Look at this. These are just elements. So remember to use this one in your homework so that when you are given that, you will see. So in the text, this is 5.3. And where we are going with this, all right, you have to bear in mind that the equation, before even we look at this, let me just share with you my whiteboard. Standard, and by the way, you'll see the standard enthalpy of what? Standard enthalpy of reaction is given by the summation of M formation of products minus N enthalpy for formation, standard enthalpy formation for reactants. So it's product minus reagent. This means summation, all right? You sum. You find the standard enthalpy formation for the product, right? There's one value. You find the standard enthalpy for the reagent, one value, and then you subtract, all right? M and N, M and N, these are the coefficient in balanced equation. So you got to look at what? You have to look at the balanced equation, all right? Look at the balanced equation and plug in this. If you are for product, if you are for reagent, that's what you will need to multiply pi. For example, we look at for oxygen, all right, we multiply by 5. We look for propane, this is propane right here, we multiply by 1, it's 1. For carbon dioxide, we multiply by 3. For liquid H2, and by the way, physical state also plays a role. You may have CO2 in solid state, CO2 in gaseous state. You can have liquid H2O or gaseous H2O. For example, here, if you look at here, please read the correct. Here is carbon dioxide. Where is it? Carbon dioxide in gaseous state. And then we also have for solid state. You don't have it here. But for liquid H2O here and gaseous H2O, so you have to look at the balanced equation and see which one you are dealing with. If is it liquid or is it gas? Is it liquid or is it gas? So in that case, we'll plug in that and have it as liquid. We pick the appropriate, they are not the same. So if allow me to just fast forward to see how this will be calculated using the equation on the whiteboard right here. All right, this is the equation you need to remember. It's the same one I have on my whiteboard using the Hess's law. M and N are the coefficient in the balanced equation. I'll give you in the exam, this equation is gonna be on the formula sheet. Know how to use the coefficient. M and N are the coefficient. Let's see, here is how to solve. We have CO2, this is the product. H2O, this is the product. So for H2O 390 what? No, CO2 here 395.5 times 3 and then plus 4. So if I'm given this, you look at liquid H2 is 285.8 and CO2 carbon dioxide is 393.5. We multiply by 3 or the coefficient in the balanced equation, So we look for each product minus reagent. One thing you don't see it here is you can wonder and say, why am I multiplying 0? This is the enthalpy, standard enthalpy formation for an element is always 0. It's always 0. So you have to know if whatever you are given in an equation is an element, make it 0, all right? So if you don't see, understand that it is 0. I know here I have some 0, 0, all right? Elements, even oxygen gas, 0. Hydrogen gas, 0. Fluorine gas, those are 0. So you understand that the 0 here is because it's an element. Crunching the numbers here, this is the enthalpy of combustion. This is enthalpy of combustion of propane gas, negative 2219.5 kilojoules per mole using the equation given here. Hopefully, you will go back, use that table. I'll allow you to use in the quiz. I see that question. I haven't made the quiz yet for chapter 5, but if you need this table, I'll share with you. But definitely, you will see it in the exam. All right. Here is another example on how to find the enthalpy of reaction. All right. Enthalpy for reaction. For that, this is what you will need to do. That if you are given a question such as this and you are asked to find the calculate the enthalpy for reaction, I wanted to look at this. I wanted to look at calculate the enthalpy change for the reaction. On the whiteboard, we have 2 moles of peroxide. This is peroxide and it's in liquid form, minus not minus, but going to 2 moles of liquid H2O plus oxygen gas, If we are asked to find the enthalpy for reaction, I'm gonna use this standard. And by the way, you see that, please don't ignore this symbol. Standard enthalpy for reaction is gonna be summation of M standard enthalpy for product minus summation of N standard enthalpy for formation for reactants. So it is product minus reagent. If I go back, to this table right here, this is the table we will use right here. So I look at liquid H2O. Liquid H2O here is negative 285.1, no, 0.8. It's 0.8 here times 2. Because of what? Because of the 2 in the balanced equation. Plus 0. 0 forward for oxygen. I'll give you that, or I'll look at the question. If need be, I may also give you that forward for element. Product minus formation of peroxide, H2O2, peroxide, hydrogen peroxide, H2O2. So we want H2O2. H2O2. This is 187. 2 times 187.8 kilojoules. 281.87. That is 187.7. That's for peroxide. All right. That is the standard ender level for peroxide. And with this will give you, all right, this will give us the ender level for formation for this. So if I have this, you see here, this is given for liquid H2O for peroxide. This is where I'm getting 187. You'll be given, of course. So product minus reagent, and turns out that this will be negative 196 kilojoules per mole. Yeah, kilojoules per mole, which is B. This is what I was talking about. Let me just blow it up here. This is what I was talking earlier on, that be careful. You may have the right equation, use your calculator wisely, but if you don't have the concept, understanding, okay, and doubt yourself and say, is it B or C? Somebody might bubble out or just select D. That is wrong. Negative 196. Always go and double check the equation, double check. You can try practice exercise 2, use table 5.3, okay? Combustion of ethanol, combustion of ethanol, okay? Combustion of ethanol. That's enough for our endolavio formation. And by the way, this is a standard. When you see this superscript node up there, it means standard endolavio for reaction, standard endolavio for reaction. And we use the standard endolavio formation, standard endolavio for what? For formation. Well, we are moving on. We are getting to second to last section in chapter 5, pond enthalpy. Pond enthalpy, okay? From the word bond, a bond is just the electrostatic force of attraction between two atoms. All right, we can always determine the amount of energy either required to break, it take energy to break the bond. Energy is given off during the bond formation. Therefore, enthalpy associated with the breakage or breaking of 1 mole of a particular bond in gaseous what? In gaseous state is just the bond enthalpy. Look at this. To break 2, this look like it's chlorine, from chlorine, Latin name for green. I know this is chlorine molecule. To break or to cleave this bond, we need certain amount of energy. We call the bond enthalpy, the amount of energy required to do what? To break the chemical bond. This is methane gas, carbon for hydrogens. We have broken how many bonds? 1, 2, 3, 4. The first one here is Cl, Cl. But in the second one, we have broken C, hydrogen, carbon, and there are 4 of them. And by the way, bond dissociation, we use this symbol. We have broken 4. We have broken 4 hydrogen carbon bond. There is one here, there is one here, there is one here, there is one here. You should be well-rounded in drawing the structural. This is the chemical formula, but this one is the structural. This will help you in looking at the bonds, but if I have the chemical formula, just Cl, this one Cl2, this is the chemical. But Cl, this is structural formula. You actually look at the structure. Structural formula will help you determine how many bonds you have, how many bonds you will break. We can just use those test literature values given for the bond dissociation. And by the way, if you need a lot of energy to break a bond, that means that bond is strong. The greater the bond enthalpy, the stronger the chemical bond. How you read this table, all right? How you read this table is that it detects or it requires 413 kilojoules per mole. That means if we have 1 mole of the CH bond, this is how much we will need to break that bond. To break carbon to carbon bond, 348 kilojoules per mole, which means we have to have a Avogadro number of what? Carbon to carbon bond. So if this is carbon, and I need to break this bond right here. For carbon to carbon, 1 mole or Avogadro number is how much it will be needed. If you look at the double bond, it is stronger than the single bond, 614, almost twice, okay? Always double bond or even triple bond is the strongest, comparing single, double, and triple. So that, triple, double, and single. Carbon to nitrogen, carbon to oxygen, carbon double bond, oxygen, carbon, fluorine, and so forth. This is how you look at it. If you have in structural form, you can look at the energy. Where we are going with this table here is we will look at the chemical compound, all right? And figure it out what are the chemical bonds we have in that one, in that compound. And then we have to sum up to see what is the bond envelope for the reaction. There is slight difference between envelope for reaction. Maybe when I get to an example, you will be able to look at how the equation is slightly different for bond envelopes from envelope for reaction. I know it's the same, but for the bonds, it is the 4 bonds broken minus the bonds formed. This is the bonds in the reagents, how many bonds we have in the reagents, how many bonds we have in the product. It is reactant minus the bonds in the product. It's not the other way around. Remember in the other equation, it was what? It was reactant, no, product minus reactant, but here it is the bond envelope is broken in the reagents minus the bonds formed in the product. And here are the summation. You'll see in an example how we use this. For example, here, if you look at the combustion of methane, all right, formation of the new bonds. Using example, all right, using example in the text, use the bond envelopes in table 4 to estimate envelope for the combustion of ethanol. So combustion of ethanol. You have to know the formula for ethanol. Plus oxygen. What are the products? Sorry, I was making my own notes, forgetting that I wasn't sharing the screen. So here is the combustion reaction. The question is, what are the possible products? Recall in chapter 4 or chapter 3 types of reactions. Okay, this is combustion reaction, and it produce what? It produce CO2, plus liquid what? Liquid H2O, liquid H2O, like that. Liquid H2O. Now, the equation is not balanced. We have two carbons here. We have two, if we put a 2 here, let's just use trial and error so that we have two carbons. We have two carbons. How many carbons, hydrogens do we have on this side? 2, no 1, we have 6. So if I put 3 here, so that 3 times 2 is 6, 5 plus 1 is 6. And then oxygen on this side, I do have 2 plus 1 is 3. And then here is 3, no, here is 4 plus 3 is 7. So if I put 3 here, this will be 6, and this will be 1. This will be 6. So you need to balance the equation first. This will not really help us in terms of estimating the change in enthalpy. We need to know whatever bonds. So here, this is the structure. Carbon bonded to hydrogen, hydrogen, carbon, hydrogen, hydrogen, this is carbon to oxygen to hydrogen. That is the structure of ethanols. With that, I see there is hydrogen, 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 hydrogen bond. So we need to know how many bonds you break from there. And we have one here, plus 3 oxygen, there is a double bond here. That's the structure for going to, you should be able, and we have 2 of them. This is carbon dioxide plus 3H, like that. So with this, you can now see what type of bonds are broken. There is hydrogen to carbon, 1, 2, 3, 4, 5. So 5 carbon to hydrogen bonds. On the reactant side, there is 1 carbon to carbon. On the product reactant side, there is 1 carbon to oxygen. There is 1. That's how you look at it. For oxygen, of course, product minus reagent, the enthalpy formation or breaking this double bond, you multiply by 3. For high oxygen carbon, they are 1, 2 times 2 is 4. So you're gonna look at that. And hydrogen to carbon, we have 2 times 3. That will give you, with this, you say product. We're gonna use this equation. We're gonna use this equation here. Product bonds form bonds enthalpies of bonds broken, which is we are breaking on the reactant side, minus what is being formed on the product side. And if we use that, she'll be able to estimate that. So here is the bond enthalpies. In this case, it is a different, not this one. This is a different one in the sense that we have ethane. This is ethane, CH2, not the ethanol. But just using the same approach, we'll have what? The ethane here reacting with oxygen gas. That's why I have a double bond here for ethanol. All right. And here, 4 moles of carbon dioxide. It's the same as the carbon dioxide I have here. We have 2 in our case. the balancing the equation. And then 6, we have that. This table right here will help you figure it out what we have. Let me just have this. So you look at this. 1, 2, 3, 1, 2, 3, 4, 5, 6. So we have carbon to hydrogen bond, so that when you look at that, there is 12. Where is 12 to carbon? Times 2. 1, 2, 3, 4, 5, 6 times 2 is 6. All right. Carbon to carbon is 2. Therefore, you see the 2 here. Carbon to carbon is 2. And then 7 carbon oxygen to oxygen minus 8. Where is 8? If you look at this, 1, 2 times 4 is 8. We are breaking this bond and we are breaking this bond. 1, 2 times 4 is 8. Oxygen to hydrogen, 1, 2. We have here and there. So 2 times 6 is 12. So if we plug that, this is reactant minus the product, D for dissociation, D for dissociation. You'll do the same thing for our example, combustion of ethanol. In this case, we have used the bond dissociation. And let me see what I have for the product one we had. The one we had for the reaction, the one we had for the reaction. This is what I wanted to show you, all right? Once you follow that, make sure you get this. This is answer, try on your own. Answer for this is negative 1255 kilojoules. Try that. It's the same thing. Using this approach for this, use the same approach in determining the enthalpy of combustion of what? Ethanol. This is ethanol. And I've shown you the structure. I've given you the structural formulas for the reagent. You know, when we say combustion, you should understand that oxygen is involved. That's why I have oxygen. Structure is O double bond. Carbon dioxide, 2 double bond on either side of carbon. Learn how to use the bond dissociation, bond enthalpies to find the enthalpy for combustion of ethanol. Or I may give you just structural formula like this in the exam, I don't know, and then you have to plug, but I cannot promise how the problems in the homework. You have to use the text in order to come up with the structural formulas and reconcile with table 5.4 to determine the enthalpy change or estimate the enthalpy for combustion, okay? Now, I want to just wrap up chapter 5, looking briefly on the energy or the food value, the energy value for the food we consume, the energy. How do we calculate the energy value, either in kilojoules or in calories, in kilojoule or in calories, energy food. The energy release when 1 gram of food is combusted is fuel energy, all right? So fuel energy, when you combust 1 gram here, the word 1 gram, we call that the fuel energy. The table here, please look at the table here. Let me just have this. If I have to blow up this, we have carbohydrate, we have fat, we have protein, and here the fuel value. Problems could be calculate the word in kilojoules or in calories. CAL per gram. You are given here 4 calories per gram for carbohydrate, 9 calories per gram for fat, and 4 calories per gram of protein. Or if you are asked to calculate in kilojoules, this is 17 point what? 17 kilojoules per gram for carbohydrates, 38 kilojoules per gram of fat, 17 proteins. For protein is 17 kilojoules per gram. So depending on the nature of the problems, please learn how you may be given, all right? You may be given the problem such as what? Such as this right here. This is what is given in kilojoules, but if we are given in different values, you'll have to plug it in the equation. Here is an example on how you may be asked to calculate the fuel value. Read or look at work example 5.4. What I want to highlight in this worked example is how you set up the problem. Look at this. If you have 8 grams, we are looking for energy in kilojoules for 8 grams of proteins. This is the conversion factor. We were given the amount of, or the fuel value for 1 gram of protein, 17 kilojoules per mole. If the meal include 26 grams of carbohydrate, you are given, or you will be given the fuel value in kilojoules per gram of carbohydrate and for fat, and then you do the same thing. You do the same thing for that. So that's how to set up. I know dimensional analysis is not something new to you. You can always plug in, set up the problems, and do the unit cancellation. And this is the total in kilojoules to 2 significant figures, all right? Please round off the 2 significant figures. 0 is just a placeholder. These had 2 significant figures. These had 2 significant figures. So we go with what? With significant figures. Well, let's see. This is a learning check, which I want us to look at. I want us to look at how we calculate. Please don't make a mistake of using the conversion factor for kilojoules. Here is the calories. If a serving of a particular ready-to-serve chicken noodle soup contains 2.5 grams fat, 14 grams carbohydrate, and 7 grams protein, estimate the number of calories in serving. So what this means is just plugging in the equation 2.5 grams of fat times 9 calories, all right, per 1 gram of fat. This will give you 22.5 calories. You do the same thing for what? For carbohydrates. This is grams of carbohydrate times the conversion factor is that 4 calories per gram or 1 gram of carbohydrate. Which is equals to 56. And lastly, 7 grams of protein, right? Protein times the conversion factor here is for every 1 gram of protein, will be 28. And then when we have here total, you add everything, right? This should be 107 calories. This is 107 calories. We don't use the kilojoules just the way we had in the example. we are using this, please take note of the conversion factor here, that if we are using kilojoules, fuel value in kilojoules, and then we'll use this, and this. But we are looking for calories, so we use 4, 9, and 4. Please, if you are given in the problem, use appropriate unit, use appropriate unit. With that, I just want to end chapter 5. All right. Please do the assignment on mastering, MyLab and mastering. I do have the posted duty. Look on the calendar on Canvas homepage. You will see the due date for all assignments, all quizzes, and the midterms. Other than that, thank you.